So let me introduce Volodymyr Vovchenko from Berkeley Lab.
So yeah, I will talk about studies of QCD phase structure, in particular at finite baryon density, which is where I think it's the most interesting region of the phase diagram as it looks right now. Yes, and studies using heavy ion collisions, which is of course very much relevant for all of you and for the field in general, because this is one, perhaps maybe the only way to access QCD at finite densities without relying on maybe uncontrolled assumptions and so on, as I will detail a little bit later. So I will maybe make only a brief introduction, because I think we more or less know like the general purpose and the goals of the field. It's the studies of strong interactions, and we think that we know the fundamental theory behind strong interactions, that quantum chromodynamics, which is a quantum field theory based on degrees of freedom called quarks and gluons, which carry a color charge. And we know that we don't actually observe quarks and gluons directly in experiment, but at small energies, these fundamental degrees of freedom of QCD are confined into composite objects called baryons, which would be a combination of 3 quarks, and mesons, which would be a pair of quarks and antiquarks. And baryons are the building blocks of matter, like for example, protons and nucleons, which form nuclei, and mesons are bosons, so they mediate the force between nucleons. That's the way to think about this. Then the scales are typically 10 to the minus 15 meters as far as lengths go, and the typical temperatures are of the order of trillions degrees of Kelvin. So these are by far the hottest fluid studied and created in the lab. The strongly interacting matter, and in particular in excited states, occurs in a number of physical phenomena. For instance, the early universe have passed through a phase consisting of essentially a quark-gluon plasma, because we know that in the early stages the universe was very hot, and it was hot enough so that hadrons were melted into their constituents, quarks and gluons. And on the other hand, there is also a number of interesting astrophysical phenomena, like interior of neutron stars is filled with dense QCD matter, and in particular the mergers of neutron stars, these astrophysical events, the outcome of the mergers is very much depends on the properties of QCD matter in cold and dense regimes, so at finite baryon density. So this is also a very interesting connection. But what is very important is that QCD matter can be studied under in a controlled environment in the laboratory by means of heavy ion collision experiments. And this is the one way to probe the phase diagram of QCD. So since we have things like energy or temperature, as well as conserved quantities, like for example baryon number, we can consider such a question like the phase diagram of QCD matter. Like what are the properties of QCD when we, on the other hand, regulate the net baryon number, or in other words, an excess of particles of matter over antimatter on one hand, and on the other hand, if we increase the energies and energy densities, and what happens with what happens with the matter under those conditions as well. And in general, we know that that QCD has some interesting features, established features, both from theoretical and empirical point of view, which allows us to make a sketch of how QCD phase diagram can and in general should look like. For instance, at very high energies, QCD has this property of asymptotic freedom, and that theory becomes very similar to a free gas of its fundamental constituents, quarks and gluons. Therefore, at high temperatures and densities, one expects a phase called quark-gluon plasma. But on the other hand, empirically, we know that quarks and gluons are not observed, that they are confined into hadrons, and if the densities and temperatures are small, then this gas of hadrons will be very dilute. And so we can think about a phase of hadron gas in the opposite corner of the phase diagram in temperature baryon density plane. And if you have these two phases which seem to be very different, their properties seem to be very different, then you can expect that there is a transition occurring somewhere between these phases. And in general, the very interesting question is, what is the nature of this transition? It can be a smooth transition, and as we now know from latest QCD, this is the case at small baryon densities, but also it can be a true phase transition. It's when properties of matter change discontinuously from one phase to another. And if that is true, then there is a critical point somewhere in the phase diagram separating these two regimes of crossover, analytic smooth transition, and the first order phase transition, and the location of the critical point is one of the major goals of the studies of QCD matter. First, we could ask a question: how far can we go from purely theoretical point of view? Because QCD is a mathematically well-defined theory of strong interactions, and if we were able to solve the relevant QCD equations, then in principle we could answer all these questions. Of course, relying on the assumption that QCD really is the correct theory, and unfortunately, this type of questions, when we go into this regime of transition between hadronic and partonic matter, they correspond to so-called non-perturbative regime. Basically, the theory doesn't have a small parameter, it doesn't have a well-defined limit, like, for example, limit of free quark and gluon gas, around which we could expand the theory and systematically calculate corrections. And for this reason, the only non-perturbative first principle method is called lattice QCD. It's a numerical solution of QCD equation on a discretized space-time grid. And there are lots of interesting technical details how to do this, but I will maybe forgo these details, but I'll only maybe highlight one of the most remarkable results from lattice QCD, which gives strong evidence that QCD really is the correct theory. And this is the calculation of the hadronic mass spectrum from first principle. This is the result from BMW collaboration from some 14 years ago, where they used basically three masses as an input to fix the parameters of the theory. There are basically three parameters in QCD for this type of calculation, and everything else then comes out as the prediction of the theory, which can be compared with the experimental data for hadron masses, which are known very well. And as you can see, the agreement of theory with experiment here is quite remarkable. On the other hand, one can also study this question, which I just introduced in the beginning, and the nature of the transition between hadronic and partonic matter when the matter is heated, like for example, when you increase the temperature of QCD matter. And this can also be done with lattice QCD, but only in restricted part of the phase diagram, namely at zero baryochemical potential. At finite baryochemical potential, QCD suffers from the so-called sign problem, which basically means that this Monte Carlo sampling of QCD or of solving this functional integral of QCD, it does not work at finite baryon density, because a quantity which we would interpret as a probability distribution becomes complex valued function at finite baryochemical potential. So for this reason, this method does not work there. But at zero baryochemical potential, this method is free of this issue. And now we have calculations since about 10 years performed at the physical point, so at physical values of quark masses, which allows us to calculate how thermodynamic properties of QCD, like pressure, energy density, or entropy density, depend on the temperature. And at zero baryochemical potential. And what has been established is that that indeed if we look at the limiting behavior in the limit of small temperatures and the limit of large temperatures, or at least as far as one so far could go with lattice QCD, then at low temperatures, the output of this numerical solution of QCD equations is consistent with models based on the picture of dilute hadronic matter. It's the hadron resonance gas model, which agrees with QCD. On the other hand, at high temperatures, where eventually the limit of quark-gluon plasma, non-interacting quark-gluon plasma is expected, the resulting behavior of thermodynamic quantities is consistent with this approach towards the non-interacting limit. And moreover, one can look in more involved and differential observables to characterize this transition between these two regimes. This transition is smooth. There is no discontinuities, so it's established this fact that in the region of zero baryochemical potential, the transition is smooth crossover, and the characteristic temperature is around 155 MeV for this transition. But finite densities are not directly accessible, and therefore this method does not offer, so far at least, answer to the question on whether there is a critical point, and if there is one, where is it located on the QCD phase diagram. But very importantly, we can study strong interactions not just using theory, but we can study strong interaction also empirically, and this is maybe even more important than theory, because like theory is all good, but ultimately we want to learn about the properties of matter from experiment, because this is the real test of the theory, and it's the real way to learn about the properties of one of the fundamental forces of nature. And so, on one hand, as I mentioned, one way to learn about these properties using experiment is to collide relativistic heavy ions. And on one hand, we can use this to test predictions of QCD in this region of small baryochemical potentials where we have these predictions. But on the other hand, we can access regions of the phase diagram which are not accessible by first principle methods, and we can also study this question of possibility of a first order phase transition and QCD critical point at finite baryon density. But maybe just before we jump to heavy ion collisions, I will just mention some constraints on the location of the QCD critical point in more quantitative terms, which we do have from lattice QCD, so from theory. And this is based on a couple of indirect lattice QCD methods to study finite baryon densities. And they are both of them are basically based on extrapolations. On one hand, you can consider Taylor expansion of the QCD equation of state around zero baryochemical potential. And you can do this because expansion coefficients are calculated at zero chemical potential. So they are accessible by lattice QCD. And the current statement coming from at least a couple of collaborations who studied this is that the Taylor expansion, which in theory should be sensitive to presence of critical point if it was close to the expansion point, but the current result indicate that there are no hints for QCD critical point above 135 MeV and at MeV over T less than 3. And on the other hand, you can also consider a different kind of expansion, not Taylor expansion, but a so-called relativistic virial expansion, where you expand instead of chemical potential, you expand in the so-called fugacities, or for a relativistic theory of QCD, the expansion is a series in hyperbolic cosines in chemical potential. And this you can also do by using clever mathematical tricks like performing calculations at imaginary value of baryochemical potential and then doing analytic continuations to real MeV. And the analysis of this kind of expansion also indicates that there is no indications for critical point at values of MeV over T less than roughly pi. Therefore, a critical point, if it exists, is likely located beyond the reach of the current lattice methods. But this brings us instead to relativistic heavy ion collisions, or the so-called little bangs, in analogy to the Big Bang, where matter, excited QCD matter, is also created and then expands. So very similar thing happens in heavy ion collisions. What we do is we collide heavy ions, which are accelerated to ultra-relativistic energies. They look like pancake before the collision. And then during the collision, we believe that QGP phase is created, at least at higher collision energies, for a transient period of time. But eventually the matter expands and hadronizes due to confinement. And eventually this hadronic matter turns into a regime of free streaming. And the momenta of all the hadrons produced in these collisions are measured in the experiment. So experiments measure the aftermath of the collisions. And by measuring this aftermath, we try to infer about the properties which took place earlier in the collisions, in particular like QGP properties. The basic control parameters of the experiment, it's collision energy. And typically when we talk about relativistic collisions, we consider energies between around few GeV, square root of S energy, and up to currently the largest energy is 5 TeV at the LHC. And another parameter is the size of the colliding region, which can be regulated by centrality selection as well as by the selection of the sizes of the nuclei which are colliding. Right. The measurements, as I mentioned, it's the outcome. So these are the abundances of all the hadrons produced, but as well as their momentum distributions. But one thing which is evident from heavy ion collisions is that they really do create a large number of particles. And this one, something one can see almost literally in the detector by looking at all the tracks emerging from the collisions. And if you have thousands of particles created in relativistic heavy ion collisions, it can be natural to think in terms of collective phenomena, in terms of macroscopic properties of matter created in heavy ion collisions, and more generally in terms of to apply concepts of statistical mechanics, because that's what you do in statistical mechanics. You're trying to describe system with huge number of microscopic degrees of freedom by few macroscopic parameters. And this more or less forms the basis of the simplest model for particle production in heavy ion collisions. Essentially, this is the ideal gas law, which was introduced more than 100 years before heavy ion collisions. But to be more precise, one typically uses the so-called hadron resonance gas model, which is a non-interacting multi-component gas of particles in the grand canonical ensemble. One uses the correct statistics like Bose-Einstein or Fermi-Dirac, and the corresponding distribution functions. They are well known and they are written here. And if you apply this model to particle production, then you can see that the majority of yields can be described on a roughly 10 to 20% level of relative error, but across, in some cases, like 7 orders of magnitude. So this is really remarkable. And this is sort of a starting point how you can put heavy ions on the QCD phase diagram. But maybe in a little bit more details from theoretical perspective, like, yes, we assumed ideal gas is like sort of the simplest model for particle production, because if you can guess the relevant degrees of freedom, you can usually get pretty far with the ideal gas law. But this model, called the hadron resonance gas model, also has theoretical foundations. And this is not simply an educated guess, but the model assumes that hadronic matter is dominated by interactions which are mediated by short-lived resonances. And if that is the case, then you can show in the framework of the so-called S-matrix formulation of statistical mechanics that the way to implement interactions between hadrons which are mediated by resonances is to leading order to incorporate resonances as non-interacting particles in the partition function of the system. And then this gives you this following structure of the pressure of the HRG model, you have contributions from mesons, both stable mesons and mesonic resonances, and you have contributions from baryons, both stable baryons and baryonic resonances. And this also indicates that hadron resonance gas model is essentially a leading order expansion of QCD pressure in the virial expansion, that if you consider high order terms like hyperbolic cosines with like 2 μb over t and so on, then this would be going beyond the HRG model. Important test of HRG model is comparison with lattice QCD equation of state that I already mentioned, that it agrees with the QCD equation of state where it should agree, namely up to and even in the region of the QCD transition. And there are extended description of HRG model, which can incorporate additional interactions, like, for example, hardcore repulsion. And this can also be done. And for heavy ion collisions, the HRG model is the basis for the thermal model of particle production. There are lots of bells and whistles which goes to applying the model to experiment, which I will not cover in detail, but nowadays there are open source codes, including my own code, which allow you to do all of these things. And I will just put a link here as a self-advertisement of my code. But let me now get back to this important application of the HRG model. It allows us to map heavy ion collisions to the QCD phase diagram, because the three parameters of the model are essentially temperature and baryochemical potential. These are the basic three parameters which you can fit to hadron yield ratios. And you can do this procedure at every collision energy of interest. And when you do this at every collision energies, what you essentially get, you extract at each collision energies the value of temperature and baryochemical potential. So that means that you can map collision energy to the QCD phase diagram. And this is roughly how this looks like when you do this, starting from the lowest energies of Hades experiment, for example. This is, I think, about 2.4 GeV square root of S, and all the way to the LHC, you get the so-called chemical freeze-out curve in heavy ion collisions. At largest energies, you are probing regions of matter which are characterized by chemical potential which is approximately 0. And interestingly, the extracted temperatures are very similar to the temperature of this QCD crossover transition, which was obtained from lattice QCD. This is around 155, 160 MeV. And this holds true for a rather broad collision energy regime. And at some point, and within the beam energy scan energies, then you have this drop of temperature and continuing increase of μb. And so the interesting fact, this matching of temperature of freeze-out and the crossover transition is that this indicates that by studying freeze-out and heavy ion collisions, you are studying properties of QCD close to the transition region. And so if this holds true over also at lower energies, then you can use heavy ion collisions to study the QCD transition at higher baryon densities or higher μb values, and therefore approach this question of the nature of the transition at higher μb values, which lattice QCD cannot answer due to the sign problem. So, and this then forms the basis of searching for QCD critical point with heavy ion collisions, and which, if QCD critical point was found in heavy ion collisions, would answer this question of what the QCD phase structure is like at finite baryon densities, because if there is a critical point, then we know that there is a first order phase transition at higher μb, and then we know that where the crossover stops at lower m'b, and basically then we really learn quite a little bit more about the QCD phase diagram. On the other hand, if we don't find any signal for the QCD critical point, this is also an important result, which can indicate that that the QCD transition is a smooth transition almost everywhere, and that if a first order phase transition is to be found, then it would likely be located in this very cold and dense regime, which one would probably have to probe with different kind of observations and experiments, like, for example, mergers of the neutron stars.
I have a question. Sorry,
Yes.
can I interrupt?
Sure.
We are looking for the proof that there is some critical behavior. Can we, for example, okay, so these are people who are like working in favor, let's say, of critical point. But is there any option, like in your opinion, to prove that there is no critical point? Sorry, but it cannot be because of.
Well, I think so. Obtaining a proof is extremely challenging, because ultimately you never know whether maybe, like, I mean, the evidence that there is no critical point from experiment would be like not seeing signals which you expect from critical point. Or another way to look at it, if you can describe all the data in a theoretical description which assumes there is no critical point. So this would be evidence against critical point. But I think it's extremely challenging to obtain a proof, because it can always be that you are simply not sensitive, or critical point is there but not quite where you probe it with heavy ion collisions. So I think the best you can do is probably obtain evidence that you can disfavor critical point in certain regions of the phase of the QCD phase diagram, but probably not much stronger than that, as far as heavy ion collisions go, at least. Because it's also possible that latest QCD methods, so the first principle methods, will mature and be able to tackle finite baryochemical potentials. And because this would be a purely theoretical analysis, then it's possible you can obtain answers from that perspective. But then you also have to trust the theory, and you have to trust all the approximations and extrapolations. So this is also very challenging.
Okay. Okay, thank you.
Yeah, sure. Yes. So now that we have established mapping of heavy ion collisions to phase diagram, and it looks like we should be able, if there is a critical point, we should be able to probe regions close to it. So we can now ask a question: what can we try to measure to probe the critical point? And one generic feature of a critical point that we know very well from phenomena, critical phenomena, not in QCD, but in ordinary fluids like water, is that critical point is characterized generically by large fluctuations. It's characterized by fluctuations at macroscopic length scales. And if you have a fluid close to the critical point, then essentially distances between atoms cover all the spectrum. So you can find atoms at all kinds of distances. And this, for example, explains this well-known phenomenon of critical opalescence, that if you have a fluid, then normally, and you shoot lasers on it, then normally the fluid, under normal conditions, it would be transparent. Then the laser will just go through it without anything happening. But if you are close to the critical point due to these huge density fluctuations, when you shoot a laser on it, it will almost inevitably rescatter, because it will always basically find pairs of atoms with distances similar to its wavelengths and so on. And this is very well known, and maybe you even seen this in your physics lab. I remember that I had this, I think, in my bachelor degree, this illustration of critical opalescence. And this is very instructive signature of a critical point. But unfortunately, we cannot do this kind of experiment in heavy ion collisions, because there is no way to trap excited QCD matter and shoot lasers on it. What we have at heavy ion collisions is well, first of all, a much smaller system than what we have here, but also it expands in vacuum, and we cannot really control this expansion. We only can measure what emerges from the collision. So this is not an option. However, what we can do instead, we can just measure fluctuations directly. We can measure distributions of the numbers of particles emerging from heavy ion collisions by simply counting events, for example, with a fixed number of let's say some particle number, doesn't matter which one at this point, and just taking the ratio to the total number of events. So this gives you the probability distribution. And if you have a probability distribution, you can then study different things, properties of this distribution, like the central moments are the most common properties, but for critical point physics, what is more convenient to look at are the so-called cumulants. And this is a cumulant generating function. It's generic expression. Cumulants is just one way to characterize a distribution, arbitrary distribution. So the leading few cumulants characterize some of the basic properties of the distribution. Like the first cumulant is the mean, the second cumulant is the width of the distribution, and the third and fourth cumulants characterize the asymmetry of the distribution around the mean, as well as the shape of the peak. But what is important here is that there is a very interesting connection to statistical mechanics and to the equation of state. Because if you look at the structure of the grand partition function in the grand canonical ensemble, it has this generic structure, which is more or less identical to the structure of the cumulant generating function. You have this log, you have the sum over all possible values of n, which would be a conserved quantum number. And the so-called the chemical potential, you can clearly see that it plays the same role as the variable t in the cumulant generating function, which implies that cumulants of fluctuations of conserved charge in grand canonical ensemble are nothing else but the derivatives of the equation of state with respect to chemical potential. And therefore, cumulants is a way to measure chemical potential derivatives of the equation of state. For our purposes, that would be QCD equation of state. And this forms the basis of a number of applications of fluctuations in heavy ion collisions. The most important for us is the search for the QCD critical point, because fluctuations are large in the vicinity of the critical point, and namely fluctuations of baryon number. So that's the conserved QCD charge. And near the critical point, one can introduce this correlation length, right? This which characterizes the scale, the length scale of the fluctuations. And in infinite system, correlation length formally diverges at the critical point, while the cumulants scale with increasing power of the correlation length. So this emphasizes this fact that as you go to higher and higher order cumulants, you become, in theory, more and more sensitive to the critical point physics. And one famous signature which has been proposed for the QCD critical point by Misha Stefanov is looking for a non-monotonic dependence of the kurtosis as function of the collision energies, because based on this on the universal properties of fluctuations near the critical point, for example, based on the Ising model, then you can, if you sketch these properties and sketch the possible trajectory of the chemical freeze-out curve, then you would expect some sort of a non-monotonicity in the kurtosis if critical point was the effect which drives the behavior of fluctuations. Then there are a couple of other applications of fluctuations, like at mu b equals 0, you could test predictions of QCD for fluctuations, and also you could try to use fluctuations as a complementary tool to study freeze-out conditions. You could fit T and mu b not to hadron yields, but to the cumulant ratios and see whether there is a consistency in freeze-out from the yields and from fluctuations. But let us focus on the critical point. This is another illustration of the signals of critical point in the cumulants. This is a model calculation of a nuclear liquid gas transition using van der Waals equation. It shows you the behavior of density of second, third, and fourth order cumulant ratios on the phase diagram in the QCD variables in T and mu. And you can see that as you go to higher and higher orders, you get first more and more sensitive behavior near the critical point, but also patterns like change of sign and non-monotonicities and so on. Now, this is how the distributions of proton number, this proxy for for baryon number, which should exhibit critical behavior near critical point. This is how it looks in a real experiment. I took it just from the STAR collaboration paper on net proton cumulants. And on the first glance, these distributions look fairly innocent. Like you just see a peak, and you really have to, like, to see something interesting, you really have to look into the tails of the distributions. And this is indeed a very challenging and impressive measurement that we can see something in the tails and in high order cumulants, and then try to put this into perspective regarding possibility of the critical point. So what we typically do is we look at these distributions, and we calculate cumulants from the moments of these distributions, and then we take ratios of cumulants, because by considering ratios of cumulants, we make these quantities intensive quantities, so they don't scale with the total number of particles, or in terms of statistical mechanics with the total volume of the system, because volume is not very easy to control in heavy ion experiments. So if we can get rid of it by considering ratio, this is very useful thing to do. And yes, this is the published results, and for skewness and kurtosis, and in particular, there are indications for non-monotonic behavior, qualitatively similar to what has been predicted as a possible signature of the critical point. So this is very interesting, and I guess the jury is still out on what exactly this means. And with data from the run 2, I think we will have more precise data with smaller error bars in the low energies, and then the behavior of the kurtosis will be more evident. But before, maybe if we cannot go to BeamNG-Scan2 data just yet, so instead maybe we could ask a question whether we can learn something more from the data which are more accurate, has smaller errors for the lower order cumulants like kappa 2 and kappa 3. And for this, we really need to do a proper precision comparison of theory and experiment. And there are lots of caveats involved if you want to compare theory and experiment, and in particular event-by-event fluctuations. And the differences are listed here. There are maybe the most important ones is that the theoretical argument is done in the coordinate space, but the measurements are done in momentum space. Then there is this assumption that one has a heat bath or grand canonical ensemble in theory. Was what we used to make these arguments about the cumulants. But in heavy ion collisions, the system expands in vacuum, so it's not entirely obvious how to make this correspondence. And then there are other issues like conserved versus non-conserved numbers, whether system is uniform or not, and whether you are dealing with a fixed volume or a fluctuating volume in heavy ion experiment. So, and maybe I briefly mentioned this, perhaps the most important conceptual issue of this assumption of grand canonical ensemble. One can try to mimic this in heavy ion collisions by considering measurements in the limited acceptance around mid-rapidity, and for technical reasons, that's basically the only thing one can actually do in practice. One can measure particles within around 1 unit at mid-rapidity, which means that the rest of the system can act as a sort of a heat bath. You can exchange particles with the rest of the acceptance. And that's on one hand, but on the other hand, if you want this to really mimic the grand canonical ensemble, you also need your acceptance to be sufficiently large that you capture all the physics, that you don't kill all the correlations that you're after. And so ideally you want the acceptance to be much smaller than the total acceptance, but the total phase space coverage, for example, beam rapidity, but on the other hand, also much larger than some typical scales in momentum space which smear the correlations. And this would be of the order of 1 unit of rapidity. And so this is very challenging to satisfy both this separation of scales simultaneously, and therefore one has to instead perform corrections and incorporate this effect that this does not really hold in heavy ion collisions. So one needs a dynamical description to probe critical fluctuations.
I have one more question.
Yes.
If I can interrupt.
Yes, absolutely.
Yeah. So when we talk about, so generally, like I understand that we have theory, which is like, sorry, this is my dog. So we have the theory, which generally like is very nice and is not affected, but by any like detector effects or
Yes.
and so on. And then we have the experiment, which is completely like, well, sometimes, yes, which is generally like limited. But if we look like at the plot which you showed from STAR experiment, when we see this like depth, oh yes, this one, everything is measured within the same experiment. And I guess this is also the same like, type of measurements and the same, corrections. Just, sorry for this. It's evening here, so it's always like this. So, so generally, if we are staying within the same experiment, and we have all the same like corrections and so on and so on, the relation, the trend, well, isn't it like it should be kept or maybe a bit shifted? But in general, like the relation between these points should stay approximately similar.
Well, that's. Yeah, so this basically the fact that systematics are the same if it's the same experiment, right? The systematic errors, at least it helps. But the issue is that because of this mismatch between theory and experiment, there are other effects which contribute and they depend on beam energy, basically. So this makes it more complicated. Like the baseline is not a unity, basically. The non-critical baseline, which I will just get to, it's not a horizontal line as function of beam energy.
Okay.
So this is sort of the issue,
okay.
At least in my view. And yeah, maybe since I'm just getting there, this will in a way answer some of these questions, right? So I listed these challenges and there are like, one can think about a couple of ways to address them. That this fact that there are the mismatch between theory and experiment, there is ground canonical ensemble there, and there is not really a ground canonical here. And then there are these other effects of volume fluctuations and so on. So the way to do this, to take care of this would then using dynamical models. So not just assuming a box with heat baths and so on, but really do dynamical modeling of the collision process. And as far as QCD critical point search goes, there are like two ways to approach this question. One is that one way is to incorporate signals of critical point and fluctuations in this kind of modeling explicitly. And so that means using hydrodynamics, it's the basis, it's the standard model of heavy ion collisions, but for fluctuations, then one has to extend hydrodynamics to describe evolution of fluctuations on top of the mean values. Then one has to use equation of state, which is input in hydro, so there is no way around it. It's always an external input. And if you want to make predictions for the critical point, then you obviously need the equation of state, which has a critical point. And to predict signatures of critical point based on, for example, assumed location in the QCD critical point, you need to have equation of state where you can tune the location. And then you can predict its signatures in this kind of fluctuating hydrodynamic description of heavy ion collisions. And this is very, oops, what happened here? Okay, this is a very ambitious effort and it's under development. There are lots of interesting developments in progress. There is, it's not complete yet to make quantitative predictions and analysis of that data just yet, but for an overview of the current efforts, I can point to this review paper here. But another strategy, and this is something I have spent some time on it the last couple of years, is to, instead of predicting signatures of the critical point, is to establish a precision baseline of the non-critical scenario. Basically, let's assume that we don't have a critical point, then modeling is somewhat easier because you don't have to incorporate critical point physics in your dynamical model. But what would be the predictions? What would be the precision predictions for this baseline? And if we then compare these predictions with the data, we could maybe see if the data are consistent with this baseline. And if it's not consistent, we can think if we can interpret this as a signature of something interesting, like a critical point. So that means we have, yes?
Sorry for this. Sorry for asking
no
so many questions. But
Mm-hmm.
so when you assume that there is no this critical behavior, it means that you have just the crossover transition and it's like goes forever, or there is some point when it somehow changes to the first order phase transition?
Yeah, no. Yeah, basically, yeah, it's what you said. We assume it's crossover everywhere, at least where we start, everywhere where we look at least in this.
Okay.
Yeah. So, I mean, if we don't go to very low energies, we cannot really say anything about very low energies. But if we look at beam energies, scan energies, we assume there is a crossover, and then we start, and then we look if the data are consistent with this assumption or not. Basically, this is the strategy. It does mean that we have to include essential non-critical contribution to proton number cumulants. And what this means is that even if we are in non-critical regime, that does not mean that production of protons is uncorrelated, is an uncorrelated production. There are non-critical sources of proton correlations. And one of them is the conservation of baryon number. Basically, if you collide 400 nucleons, then the outcome is 400 nucleons or 400 net nucleons, right? You cannot produce an excess of baryon numbers in any QCD process. And that means that if you were able to measure baryons and antibaryons in full space, then the net number would be exactly, well, counting spectators as well, but yeah, the net baryon number would be exactly the input. So there would be no fluctuations at all. So this is one way to see, or in other words, if you have a baryon, if you have an excess of baryon in one region of the phase space, then you must compensate it with an antibaryon produced somewhere else. So this is sort of how baryon conservation creates correlations between particles. And the other essential and non-critical contribution that is the interactions between hadrons, which cannot be attributed to critical point. And in particular, is the well-known phenomenon of hard-core repulsion, that in nucleon potential, we know very well that there is a repulsion at short range, and this also creates correlations. So these two effects are incorporated on top of realistic hydrodynamic simulations. So this is just one slide about the repulsion, and it's incorporated by means of excluded volume. So basically, we incorporate this repulsive core of nucleon-nucleon interaction by basically performing this van der Waals-like procedure. One substitutes the total volume in the system by the available volume, then in the one canonical ensemble, one obtains this kind of transcendental equation for the partial pressure of baryons. And without going into detail, I will just mention that if you include repulsive interaction, you suppress fluctuations of baryon numbers in the grand canonical ensemble as well. And at zero chemical potential, you can match this parameter, the excluded volume parameter, such that you are consistent with latest QCD data. So yeah, this is another part of that non-critical scenario. We would not only want it to be like a crossover scenario, we want this to be a crossover scenario which is consistent with QCD equation of state from lattice that we have at mu b equals 0, at least in the freeze-out regime. And so this excluded volume effect is one way to achieve that. And the value is about 1 cubic Fermi, is what matches the lattice data. This is used in the calculation. But the calculation, it's the 3D hydro simulation using music. It has been constrained to the bulk observables, like distributions of net proton number, as well as the RPT spectra. Consistent with the notion of non-critical scenario, we use the crossover equation of state, so no critical point, but it is based on lattice QCD, so based on Taylor expansion of lattice QCD. Then at the end of hydro, one performs the so-called particleization. So we transform the hydrodynamic fluid and fields into particles. And this procedure contains, this procedure is extended to incorporate not only mean numbers of particles, but also fluctuations which are consistent with this effect of baryon exceeded volume on one hand, and on the other hand, we also perform correction for the global baryon conservation. So for the correlation stemming from the baryon conservation, the other essential and critical contribution to proton correlations. And this is then the outcome of this modeling, dynamical modeling of proton fluctuations in non-critical scenario. And we see here is comparison of net proton ratios of third to first order and first to second order cumulants. And we see that we can, that maybe the third order is a little bit more interesting because the error bars are so much lower, and we can make some quantitative statements here. And basically, when we incorporate both baryon conservation and repulsion, it's the full red lines here, we obtain quantitative description above 20 GeV square root of S, but at lower energies, here one sees that the data show an excess of skewness over the baselines. So we still see a suppression, but it seems that something is changing as the collision energy is decreased below 20 GeV. So one can look at this in a little bit more detail by considering, in addition to cumulants, the so-called factorial cumulants, which is a complementary way to look at the distribution, and they are maybe more interesting because higher order factorial cumulants probe presence of correlations in general, and in particular of multi-particle correlations. For example, if you have no correlations, then C2, C3, and C4 would be all equal to 0. And we see that it's still not easy to say much about multi-particle correlations, third and fourth order, because there are still fairly large error bars. But these deviations below 20 GeV square root of S in two-particle correlations are more evident in this observable, as shown here. And we really see that this excess of skewness in the data relative to critical baseline is rooted in the fact that the data show enhancement of two proton correlations over predictions from the baseline at energies below 20 GeV square root of S. And one could argue different possible effects which can be responsible for that, but by far the most intriguing one is the possibility that we are approaching the critical point, because generically two particle correlations become large in vicinity of the critical point. And you could imagine that as you decrease collision energy and approach the critical point, then first you are dominated by baryon conservation, which gives you negative two particle correlations, but then the slope changes as you approach the critical point, and you have this deviation from the base. So this is one possible explanation, but obviously one has to look in much more detail to say more. And then this is sort of questions which will be answered in the future, I think, in light of the ongoing and future measurements and experiments, because they all look into this region more or less between 2.4 GeV and 7.7 GeV. At 2.4 GeV, we already have an intriguing hint from the Hades collaboration. They measured cumulants of proton distribution, and in particular, they measured this huge variance of proton distribution, the scaled variance of more than 2. This is really very dramatic deviation from the baseline, which simply continues to predict monotonic decrease of and suppression of the variance with respect to unity. Then there is obviously the StarFix target program, and with data also published. I believe there is at 3 GeV, it's around 1 point something, the scaled variance. So one could see that there is a sort of a trend going up here. And if indeed, the one naive but also intriguing explanation that I just mentioned is that this large fluctuations is a signature of a critical point. If it's indeed the case, and this is what causes it, then this would indicate that the critical point could be located in baryon-rich region of the phase diagram, close to the freeze-out conditions at Hades, which would be the following values of T and mu B. Interestingly, some of the effective QCD approaches, based, for example, on holography, predict the possibility of a critical point more or less in this baryon-rich region of the phase diagram. But this is something which, has to be studied with future experiments. But what we can say about what we have learned so far from the experiments and data we have is that critical point is disfavored at high energies, or alternatively at large, a small mu B over T, because the data at square root of S more than 20 GeV is consistent with non-critical physics, with precision calculations of non-critical baseline. This disfavors critical point at mu B over T less than 2 or 3, and this is consistent with what we know from latest QCD and extrapolations from zero chemical potential. But interesting physics at high energy, at high densities, high baryon densities, will be probed by future experiments and by future data. Intriguing hints from Hades, for example, and from 3 GeV, and even from this excess of correlations from beam energy scan that I also described. So these are all interesting, intriguing hints, which might be consistent with critical point. We will see. But also interestingly, that as we go to lower energies, we also go into the regime, which is essentially overlaps with the physics of neutron star mergers. That when neutron stars collide, they as simulations of those phenomena show, they also create excited matter of QCD with temperatures which may reach like 50, 60 MeV, but also chemical potentials are of the order of 1 GeV or so. So this may very well overlap with the experiments at lowest energies from relativistic heavy ion collisions. But in general, there is a common ingredient between these two phenomena, that QCD equation of state defines to a large extent what happens in heavy ion collisions. And it also defines things like gravitational wave signals in neutron star mergers. And so if we want to understand the behavior of QCD matter at large baryon density and maybe build a theory or a model for that, it has to be consistent with both phenomena. And this will be very interesting to see how these two fields will inevitably overlap in the near future. But with this, I come to my summary. So strongly interacting QCD matter under extreme conditions undergoes a crossover transition to quark-gluon plasma at trillion Kelvin degrees at small baryon chemical potentials. And it behaves like a fluid described by Hydro. This is something we already know pretty well, but the phase structure of QCD matter at finite baryon density is still largely unknown. We only know that there is no real phase transition at high energies. But fluctuations in heavy ion collisions are a powerful tool to explore the QCD phase diagram. And analyzing the data from beam energy scan, we see that above 20 GeV, the data are described by non-critical physics, but possible critical point signals are seen at lower collision energies, both from beam energy scan as well as from other measurements like fixed target at star or Hades. But more evidence at lower energies will come soon from future experiments, as well as from connections from neutron star phenomena. So I think there are very interesting times ahead in that regard. But with this, I would like to thank you for the attention. And
thank you a lot for the great talk.
Yeah, Volodymyr, the very nice talk. Yeah,
thank you.
I learned a lot. Could you give some comments on your last few pages on the like neutron star merger? Like for this topic, I think the signals from the mergers of neutron stars I can think about is like the photons and the gravitational wave. Yeah. Do you know how to, based on those signals, to like see a signal of phase change, transition?
Yeah. So the signature was which has been studied and was proposed is the analysis of the ring down of the gravitational waves. That depending whether you have a strong first order phase transition or a smooth crossover, basically the amplitude of the ring down is different, and I think it's still below the sensitivity that of the observations which have been done so far. But with larger sensitivity, basically whether you see a long ring down or a short ring down is it can be used as an evidence whether you have a first order phase transition or not. I don't think there was anything about critical points specifically, but basically the statement would be that if you see evidence of first order phase transition from neutron stars, and you know that there is a crossover at high energies, then there must be a critical point somewhere in between. Basically, this is the connection.
Oh, okay, thank you. Oh, what's the word ring down? May I ask?
Yeah, it's so you have this. Yeah, basically it means that the amplitude of the waves decreases with time. So they called it ring down, more or less. I think.
Okay.
I mean, maybe I'm butchering some terms here, but that's what I remember. Yeah.
Okay, thank you. I have another question on. So when we say smooth transition, do we mean like higher order of phase transition, like second order or third order, or something else?
Yeah. So in this context, from the latest QCD, it really means analytic crossover. So there is no discontinuities in any order. And the way they established that is that they studied finite size scaling, because you have different finite size scaling behavior, whether you have a real singularity somewhere, which would be discontinuity, for example, in high order derivative, or whether you have everything which behaves smoothly. So usually you really mean that there is no discontinuities even in high order derivatives when you say crossover.
Okay.
By definition, it's not analytic if there is a discontinuity in any high order derivative, then it's not analytic, basically.
Okay, thank you.
Yeah, thank you. Yeah, very nice talk. So I actually have a question that's kind of like related to what Maria asked when you're giving the talk. So when you see a non-critical baseline, so that it is based on the analytical like smooth transition. But we do see that for like higher baryon densities, namely, which is like lower energies, it also somehow comes back to the baseline. It is near the critical point where things start to fluctuate a lot. I don't know if I'm using the right terminology here, but like things start to behave. So is there any like support or like theoretical support to say that like when we are like far from the critical point on the other direction, on the like high baryon?
Okay. Yes. Yeah. So in theory, yes, but in practice, it's a bit more complicated because maybe there is the sketch of the phase diagram here. Basically, so there are some issues with lower energies. Is that on one hand, this hydrodynamic modeling at large baryon density is much more complicated than at high energy, and so this makes it more difficult to even to trust hydro and to establish the baseline in the first place. And second issue is that basically at some point you reach another critical point from nuclear matter when you decrease the collision energy. The critical point that we know exists as opposed to the QCD critical point, and for this reason it's there is like there isn't really a clear baseline here anymore at the low energy regime. Like if there was a critical point, let's say at relatively low mu b over t, then we would probably have this regime where we are back at the baseline, and then we could say that critical point is really just some perturbation in small range of square root of s. But I think that because critical point, if it exists, is at fairly high mu b. There is it's hard to establish the baseline on this other lower end of square root of s.
Okay, thank you.
Yep.
Okay, I guess there are no more questions. So I would really like to thank you.
Okay, thank you.
Okay.